citrate coming in by a condensation reaction through oxaloacetate and acetyl-CoA. Now, the acetyl-CoA is coming from the degradation of pyruvate through the dehydrogenase complex, the pyruvate dehydrogenase complex. But again, I want you to keep this in mind because this little issue here in regards to consuming NAD or moving NAD from the mitochondria to the cytosol is one of the issues we're going to contend with, hopefully today, if we can get to it in regards to thinking about how we are moving that NADH and what it's actually going to cost us in regards to our overall efficiency of this system. But ultimately, we're seeing the release of carbon dioxide coming from this particular cycle, as well as all these electrons from 4 different points within the. Remember, we have some of the non-reversible reactions here. We have a non-reversible reaction here, which is the commitment of the oxaloacetate to acetyl-CoA to make citrate. And then when the rest of the reversible until we get to that particular alpha-ketoglutarate and isocitrate situation in bringing through that second carbon dioxide release. But again, the electrons are being moved through with their particular proton contributors to NADH and FADH2 as a capacity to move those electrons safely to other systems. And we'll see that a little more today and in the coming weeks. We want to really also think about this particular enzyme system for the first step, which is a key regulatory component in the process of entry of molecules from glycolysis into the TCA cycle through the pyruvate dehydrogenase complex. We have a similar complex also within the TCA cycle, the alpha-ketoglutarate dehydrogenase complex, which does the same kind of thing, releasing CO2 as well as generating NADH2. So those dehydrogenase reactions seem to have a common component in regards to allowing us to make NADH, and there being multiple enzyme complexes. So again, just to highlight again, coenzyme A, and it's this little thioactive group that we're going to be utilizing to remove or to combine the remaining 2 carbon constituents from the pyruvate as it's degraded by the pyruvate dehydrogenase complex to first give us carbon dioxide, our first CO2 release from the carbohydrate backbone, and giving us that acetyl group to then actually attach itself to the thiol ester reactive group in regards to forming acetyl-CoA. So again, when we see this moiety, with this group, we're basically focusing on with the attachment to the thiol ester, but it's also contributing a very large component to this system. We talked a little bit about substrate channeling, which is a very important role in regards to this case with the acyl lipolysine and that disulfide bond that needs to be oxidized to accept the hydroxyethyl position from the TPP and allow us to then go through that process and basically displace the acetyl group with CoAsh to give us acetyl coenzyme A. But then we've got to contend with this reduced disulfide bond, and we have to regenerate that disulfide linkage, and we're going to take the electrons and the protons and sink them into FAD to make FADH2, but we're going to recycle that to allow us to give us more electrons and also the production of NADH, which can be utilized again as a carrier for energy, as we illustrated here. So again, just a little bit of a summary in regards to what we're talking about today, and also having to understand clearly where the carbons are going in this particular in this particular pathway. And so again, going from acetyl-CoA to citrate to isocitrate through cis-anaconate, and then going to alpha-ketoglutarate from isocitrate to succinyl-CoA to succinate to fumarate to malate to oxaloacetate. So we're going from adding the 2 carbons to the 4 carbons to give us 6, and we'll start seeing a decrease in the carbon numbers as we release it as carbon dioxide from the alpha-ketoglutarate dehydrogenase complex and also the isocitrate dehydrogenase complex in regards to giving that capacity to release carbon to decrease our carbon constituents from 6 to 5 to 4, which then continues as a 4 moiety oxaloacetate to then be recondensed with acetyl-CoA, with the CoAsh being the leaving group, and giving us those 2 additional carbon moieties on that 4 to give us a 6 carbon constituent. So again, we need to understand again that clock face, that we have a reversible reaction, a commitment stage, as well as a number of irreversible reactions from usually about the 4 o'clock to 5 o'clock, 4 o'clock to 6 o'clock position in the clock face, in regards to a commitment to moving these molecules, particularly the alpha-ketoglutarate, as we'll see this guy come back to us in several different forms and shapes and different metabolic pathways. Alpha-ketoglutarate plays a key role in the commitment because we can take this off and do things with it, or we can commit it to its transformation back into a 4-carbon constituent, rearranging the bonds and getting more NADH and FADH2, and in this case GTP, from that particular system. Okay, so we're talking about the various steps, and we were getting to, where were we? The blockers. So as I said before, these are really important to kind of consider as they illustrate the specificity and selectivity of the enzyme systems. In this case, we have malonate, which is basically a very strong competitive inhibitor because it looks like succinate, just shortened by a carbon constituent in the middle. It still has the capacity to be able to bind to the enzyme and causes inhibition. Now, we also show clearly that with our enzymes, there's also, again, this issue of stereospecificity. So here we have a trans and a cis carbon dioxide or carboxylic acid on the fumarate and the malate, which is a derivative of malate or a isomer of malate, in regards to having different types of shapes and forms in regards to the malate D and L forms, which again illustrate this issue of stereospecificity. With that stereospecificity, we're going to get selectivity. So in this case, we have a cis and a trans component, which basically this guy, the fumarase, has the capacity to bind and transform this molecule, but does not have the capacity to do the cis form. So again, stereospecificity becomes a very, very selective component in some of these particular enzymes. But again, we have some needs to ensure that stereospecificity is maintained throughout the biological system, because it might produce different isomers which may not be functional in later pathways downstream. So we want to specifically look, and we've seen this particular reaction already in regards to the malate shuttle. If we go back to about 2 or 3 weeks previous, where we see the final steps in regards to producing oxaloacetate. Now, oxaloacetate, as I said before, we already know oxaloacetate plays a role in the phosphoenol pyruvate production, as well as the movement of the NADH out of the mitochondria into the cytosol. So this particular guy here, L-malate, through the malate dehydrogenase, is an interesting reaction because it is actually one of the most energy consuming reactions at positive 29.7 kilojoules per mole. It consumes NAD plus to make NADH as well as protons. It's a reversible reaction. So if we're going the other way, obviously we'd get negative 29.7 kilojoules per mole, but we're moving it to oxaloacetate. So what we see here is basically how we remove those 2 protons from malate, forming a double bond in this carbon position and allowing those 2 hydrogen moieties to be integrated into the NADH and 1 as a surplus proton. Now, this allows us to have regeneration of oxaloacetate. And our reaction process, as I said, is favoring the left-hand side. And in this case, we need to be able to provide the energy from some of those negative delta G reactions within the TCA cycle as a coupled reaction to allow this to move forward. So again, this is an energy requirement. So if the energy is not there, we are not going to cause the regeneration of the oxaloacetate. So again, keep that in mind. So the reaction which the oxaloacetate reaction feeds is a highly exergonic reaction in regards to the citrate synthase. So we can have that energy system being able to feed some of this, which I think is above like 33 kilojoules per mole. So the overall process in regards to the production of oxaloacetate from malate is favored in the production of oxaloacetate because we need that to be balanced to the incoming acetyl-CoA coming from the dehydrogenase complex, the pyruvate dehydrogenase complex. Without that continual balance of oxaloacetate and the acetyl-CoA coming in, we are not going to produce a citrate, and therefore we're going to put a hold on the TCA cycle in regards to the production. We don't need the TCA cycle to actually feed the production of oxaloacetate, as we'll see, and you might start thinking about the structure of oxaloacetate specifically in regards to what does it look like in regards to potentially an amino acid. We'll get to that one a little later on. So we then have this capacity to favor the production of oxaloacetate to feed the TCA cycle. Now, this is an illustration of some of the things we're going to look at today in regards to radio labeling. And so in this case, we might have radio labeled acetate coming in. And we can then condense that with oxaloacetate to produce then the radio-labeled citrate. Now, interestingly, we have two capacities to undertake the reaction in regards to the potential of producing two structural forms of isocitrate. But what we see is basically a preference in regards to the labeling situation that only one product is formed, this upper number one product being formed in regards to the way it's attaching itself to the oxaloacetate. Okay, it's not causing this attachment here and forming a double bond oxygen on this particular carbon. So this kind of gives us again illustration of susceptible bond stereospecificity within these particular reactions. And we're going to come to have a little bit more understanding of this as we specifically look at radio labeling of the individual carbohydrates coming into the TCA cycle as the form of acetyl-CoA and going through the various phases of degradation to give us the release of those radio-labeled carbons. And just remember, we can trace these radio-labeled carbons now specifically in the production of carbon dioxide, because as we see our constituent going in from the 2-carbon and 4-carbon constituent, 2-carbon acetyl-CoA, 4-carbon oxaloacetate, we're going to see that decrease in carbon loading going from the 6 to the 5 to the 4 carbon as a result of removal of carbon dioxide. And the only way we're going to see that is through this enzymatic system. Okay, but we'll have a little bit more look at that later on. In our biology textbooks, we might have seen a number in regards to what actually is produced in aerobic oxidation of a glucose moiety by the pyruvate dehydrogenase complex and its entry into the citric acid cycle, as well to another system called oxidative phosphorylation. We'll get to that towards the end of these lecture series. So we already know we're going to have a number of commitment stages occurring within glycolysis, which is going to consume ATP because we're going to phosphorylate that glucose, and then we're going to phosphorylate that phosphorylated fructose to become doubly phosphorylated in the form of fructose 1,6-bisphosphate. So we have our consumption here in regards to our negative priming reaction, but ultimately, as you can see here, we produce a very large amount of NADH, particularly NADH. We produce a small amount of FADH2 from this particular biological system. This is going to change when we start looking at fatty acid oxidation. And we produce, a reasonable amount, enough to pay back our commitment stage, and then have some over in the form of ATP or GTP. Remember, ping pong, we can move that GTP to ATP. Now, there is one anomaly here, and sometimes you might see it in the biology textbooks where they'll say 30 to 32 ATP are formed in regards to the number of reducing equivalents and ATP being produced. Now, we equate a calculational component. You need to remember this number, that 2.5 ATP molecules per NADH. And we get 1.5 ATP molecules per NADH2. So again, we have a direct lineation to how much ATP is going to be produced by the utilization of that NADH or that FADH2. If we add this all to our tally, we should get 30 to 32 ATPs formed. But there is a little consequences here in this guy here, in the glycerolaldehyde 3-phosphate to the 1,3-bisphosphoglycerate, because there is a issue of transport. And we're going to come back to this a little later on in regards to how we move, importantly, the NADH out of the system and feed it into the cytosol, because this, in the most cases, particularly the TCA cycle is happening inside the mitochondria. But here we have the capacity to keep that NADH into the cytosol for cytosolic use, but also supplement that through a transport system that is going to deplete the system of 2 NADHs. So that's why we see the 30 to 32 number, because sometimes in some systems this is not undertaken. So again, depending what type of organism you are, what type of system you are, sometimes you may not be able to supplement the NADH concentration in the cytosol, so therefore you'll have 32. But if you have the capacity to supplement that cytosolic NADH, you're going to have 30. So again, keep this in mind in regards to the individual steps, because we've actually studied every single one of these steps in regards to the glycolysis and now the TCA cycle. But again, note this. We are taking a 6-carbon constituent in the form of glucose, and we're bringing it through to 2 molecules of pyruvate. Those 2 molecules of pyruvate will produce 2 molecules of acetyl-CoA. So then it has to be matched with 2 moieties of oxaloacetate to fully consume the 2 moieties of acetyl-CoA coming from that glucose. So again, those ratios that we talked about in the past become more apparent and more specific in regards to understanding where they're going in regards to the breaking down of a 6-carbon constituent to produce 2 carbon constituents as the form of acetyl-CoA, to then bring that into a cyclic system to allow us to circulate those carbons around, releasing carbon dioxide off in the appropriate concentrations in regards to the supply of that 2-carbon constituent in the form of acetyl-CoA. So please keep that in mind, because we're going to come back to that time and time again in regards to the balance of energy in regards to these combined biochemical reactions. So we've got the overall aspect in regards to where the NADHs are coming from, where the isocitrates are coming, where the GTP is coming from. This clock face is a little bit off, where, so we've got our condensation reaction with oxaloacetate. We then see the first NADH coming off with the isocitrate dehydrogenase complex, having that carbon dioxide being released, and the formation of NADH and the consumption, importantly, of NAD+. And remember, the consumption to produce an electron carrier has to be matched, meaning you cannot just make NADH out of thin air. You have to have the NAD+ being present. So you can sink those electrons and utilize those protons to produce the appropriate electron carrier. And again, we see this happening again with the alpha-ketoglutarate dehydrogenase complex, which is going to also cause the release of CO2 and also produce NADH. And again, these steps are non-reversible. Succinyl-CoA, we've now got a priming reaction to have that CoAsh consumed to make succinyl-CoA to give us a great leaving group, as well as capacity to use that phosphate to produce GTP from GDP and give us an ATP equivalent. And then we have that succinate chiral molecule, which basically we can then rearrange the bonds through a hydration and dehydration reaction. And this is where we get our only electron carrier in the form of NADH2 from this particular cycle. But we are going to see other sources of NADH2 coming in to our pool for oxidative phosphorylation to make ATP at a later stage. So we're going to see that become a dominant feature in the form of electron carriers. But noting again the difference, we get more ATP from NADH than we do from FADH2. So this is 1.5, this is 2.5 as I illustrated here, okay? So we then go through our production of our final NADH from the conversion of malate to oxaloacetate, which is then the capacity to then form the condensation reaction with the carbon-2 moiety coming from pyruvate in form of oxaloacetate via the pyruvate dehydrogenase complex to form citrate. So again, this particular cycle going around and around, it's always going to cause the release of carbon dioxide, cause the generation of NADH and FADH2, as well as GTP. So again, the general idea of this particular system. And you're going to have to know the individual structures and the reversibilities and where you're getting the carbon dioxide and the NADH, GTP, and FADH2 from, because that's going to be important to correlate that to our next stages in oxidative phosphorylation. So some of the terminology: cellular respiration, the citric acid cycle, the oxidative phosphorylation, which we'll get to a little later on, but I want to just keep the bigger picture. We have the oxidative decarboxylation reaction occurring in the first stages of the pyruvate dehydrogenase complex, and then the illustration of what that provides us in regards to substrate channeling. We've got to know and understand the structures and the reversibility reactions of the TCA cycle. The importance of oxaloacetate. We've already introduced this to you in regards to oxaloacetate being also substitutional to produce phosphoenol pyruvate. We have the pyruvate dehydrogenase complex, the basic mechanism with those thiols in regards to the disulfide bond formation, and then the hydroxyethyl group coming off the remaining component of the decarboxylated pyruvate, because that's the first stage where we're going to see carbon dioxide released, is actually the pyruvate dehydrogenase complex. So, people forget about that in regards to that enzyme is producing carbon dioxide, and that carbon is a direct degradation of pyruvate, going from a 3-carbon constituent now to a 2-carbon constituent in the form of acetyl-CoA. We're losing a carbon there through carbon dioxide. This is where we're going to see our particular carbon release, and this is where we see our breath coming from in the exhalation of carbon dioxide from our lungs, because this is all through the process of metabolism. We're going to have a look, and as I said, you need to understand the issue of the 30 versus 32, but we're going to come back to that a little more detail when we look at transportation in the malate aspartate shuttle. So just keep that in mind, the malate aspartate shuttle, where we're going to see some interesting transformations, again, through some amino acids and our friend oxaloacetate. So we've finished that particular lecture. Now we're going to look a little bit